Welcome back to the Deep Dive. Today we are taking a truly ambitious journey, undertaking a systemic deep dive that spans, and I mean this literally, the microscopic world of the electron.
All the way up to the most intense global policy debates.
Exactly. We're talking nuclear energy, semiconductors, and even the very real threat of weaponized deepfakes.
It's a scope we have to take, really. The source material we've synthesized for you today comes from a comprehensive review across engineering, policy, and, high-level administrative concepts.
So what we're doing is basically handing you a master key to understanding these incredibly complex systems.
That's the goal. You'll move beyond the headlines and really grasp the fundamental trade-offs that are driving decision-making in a rapidly developing, energy-hungry economy like India's.
Our mission today is kind of twofold. And it's all about linking the physical world to the policy world. First, we need to ground ourselves in the core, often overlooked engineering principles that govern your daily life.
How electricity actually works.
Yes, how it actually flows, why things work, why they fail. Then second, we're jumping into the massive structural policy challenges.
And this is where it gets really complicated. The energy paradox, the chronic debt crisis facing the discoms,
And the strategic need for these high-stakes technologies like small modular reactors and advanced semiconductors that will, at the end of the day, determine India's entire future trajectory toward net zero 2070.
Right, because you cannot effectively fix the national policy architecture without a rigorous understanding of the engineering and physics constraints on the ground.
You have to connect the two.
You have to. We need to seamlessly move from the circuit board to the state capital, understanding how a voltage drop in a distribution line directly impacts the economic viability of a private generator 1,000 miles away.
Okay, let's unpack this. Starting with the absolute basics that literally make our homes run. We're talking about the very nature of power, starting with the invisible carriers that make everything possible. So when we talk about electricity, we throw around terms like electric charge and current. Electric charge, okay, it's a fundamental property of matter. But when that charge moves, which is what we call current, it is almost exclusively the movement of electrons. Why is that?
It's a great question.
Why not the bigger, heavier protons or nuclei? Why aren't they part of the flow?
It's a fundamental question of material science, really. If you imagine a copper wire, the protons and neutrons are they're tightly bound within the nucleus. They form this rigid, massive lattice structure of the solid material itself.
So they're basically the scaffolding. They can't move.
Exactly. For a proton or a nucleus to move, you would need a colossal amount of energy. You'd effectively be destroying or physically moving the wire itself.
So the positive charges are just locked in place.
Precisely. The movement is entirely due to the outer, or what we call valence, electrons. These electrons are very loosely bound to their parent atoms. A potential difference of voltage provides just enough kinetic energy to cause these electrons to sort of drift through the material.
And that drift is the current.
That is the flow we define as electric current. The mass difference is enormous, and their structural mobility is really the decisive factor here.
And the principles that govern this flow are captured in these foundational conservation rules, Kirchhoff's laws. They always look so intimidating in textbooks with the sigma notations and diagrams.
But they're really just elegant statements about conservation.
Simple physics bookkeeping, right?
That's all they are. Kirchhoff's current law, KCL, is basically the conservation of charge. It just says that at any junction in a circuit, the total current flowing in has to equal the total current flowing out.
So if you have 5 amps coming into a point.
You must have 5 amps leaving it. You can't just create or destroy charge instantaneously. It flows from one path to the next. Simple as that.
Okay. And KVL, Kirchhoff's voltage law.
KVL is all about the conservation of energy. It states that if you trace a complete closed loop in a circuit, the sum of all the potential differences, so the voltage sources, which are your energy inputs, and the voltage drops, the energy being used, has to be zero.
It all has to balance out.
It has to balance. It's a statement that energy is finite and must be accounted for. The energy your battery or wall socket supplies has to be completely used up or stored by the components in that loop.
These laws really came into play during the famous War of Currents, didn't they? The big battle between AC, alternating current, and DC, direct current.
Oh, absolutely.
Edison's DC was a functional system, but Tesla and Westinghouse's AC won that historical fight. And it came down to a single word: efficiency.
And that efficiency is rooted entirely in one simple physics relationship: the power loss in transmission lines.
The I²R relationship.
Exactly. Power loss is proportional to the square of the current. That's the I². multiplied by the resistance of the wire, the R. Edison's DC system had to deliver power at the same low voltage the consumer used, which meant the current, the I, had to be really high to get any meaningful amount of power.
And high current means massive losses, even over short distances.
Massive. And since the loss is proportional to the square of the current, if you double the current, you don't double the loss. You quadruple your heat loss.
Wow.
This meant DC power plants had to be located, almost every mile. It made the system decentralized, incredibly capital intensive, and just fundamentally wasteful.
But the AC transformer was the game changer. You could step up the voltage, which, in turn, inversely reduces the current for the same amount of power. And that reduction in current is where the magic happens.
That is where the massive magnitude shift happens. Let's say you step up the voltage by a factor of 10. The current drops by a factor of 10, but because the losses are squared,
the I squared R loss drops by a factor of 100.
100. It's a huge difference. This meant power could be generated centrally, maybe hundreds of miles away at a big hydro dam, and then transmitted with just minimal thermal loss. That exponential reduction in loss made centralized power generation and long-distance transmission economically and physically viable.
And that's what sealed the deal for AC for over a century.
It secured its dominance, yes.
But here's where it gets really interesting, because DC isn't just surviving. It's making a powerful, really strategic comeback.
It is. We see DC in two crucial areas now. At the consumer level, almost everything digital we use, your phone, your laptop, it all runs on DC internally.
Which is why you have that little power brick, the converter.
Right. And because of that, you're starting to see large DC microgrids being planned for things like data centers or big commercial complexes, completely bypassing the AC to DC conversion losses.
And what about for the main grid itself?
For the grid, we're seeing the massive application of HVDC, or high voltage direct current. Now, while AC is still better for medium distances and for tapping off power to local areas, for bulk power transfer over extremely long distances.
Like what kind of distance?
Say, connecting a massive solar park in Rajasthan to a load center in Karnataka. That's over 1,000 kilometers. Over that kind of distance, HVDC often results in lower overall losses.
Interesting.
It's a very targeted, highly efficient solution for bulk power transfer, especially across, say, international borders or for deep-sea transmission.
So let's zoom in from that continental transmission right down to the plug socket in front of you. Take the standard 3-pin plug. The top pin, the earth pin, is always thicker and longer. It seems like a tiny detail, but it embodies two critical engineering safety principles.
It's pure engineering by design intention. The first reason is about the pin's length. It's intentionally longer so that when you insert the plug, the earth connection is made first.
Before the live power.
Before the live power. And when you pull the plug out, it's the last one to break contact. This guarantees the appliance is grounded, and any fault current can be safely diverted before power is connected or disconnected. It's a simple mechanical failsafe.
And the second reason is its thickness.
The pin is thicker for two related reasons, both for protection. First, the size physically prevents you from accidentally forcing the ground pin into the smaller live or neutral holes. It's a simple mechanical barrier against getting a shock.
Okay, that makes sense.
And second, a thicker conductor inherently provides a much lower electrical resistance path. So if a fault happens and current surges to that earth wire, the super low resistance ensures a massive fault current flows instantly.
Which trips the circuit breaker immediately.
Extremely rapidly. It maximizes safety by minimizing resistance. It's brilliant, simple design.
That's a great example of design being dictated by risk mitigation. Let's talk about controlling the flow inside our homes. I remember those old fan regulators, the ones with the clicks. They would hum and get warm.
Oh, yeah.
I always felt like they were actively heating the room just to slow the fan down. It felt like this terrible thermal tax on summer comfort.
That's because they were doing exactly that. Those old regulators were basically resistance boxes. They just used a big resistive element to drop the voltage going to the fan motor. All that energy that wasn't being used to spin the fan was, in fact, dissipated as heat.
So it was just waste, a massive inefficiency.
A huge waste.
And the modern ones are sleek, they stay cool. How have we solved that problem technologically?
We moved into the world of power electronics, using components like triacs or thyristors. Instead of dissipating the energy as heat, Modern regulators work by chopping the AC waveform.
What does that mean, chopping?
They switch the power on and off very, very rapidly during each cycle. This reduces the effective voltage and power that gets delivered to the fan. Since they aren't absorbing and dissipating energy continuously like a resistor, they're just exponentially more efficient.
Okay, moving on to another unsung hero component, the capacitor. We all know it stores energy, but it's an absolute workhorse in the real world. Let's detail its triple role.
Its three roles are essential for system viability. The first, as you said, is for smoothing and filtering. In any AC to DC conversion, like in your phone charger, the output is naturally fluctuating. It's kind of lumpy.
Right.
The capacitor acts like a tiny, temporary energy buffer. It absorbs the peaks and fills in the valleys, ensuring a smooth, steady DC voltage for your sensitive electronics.
And what's role number 2? I know this is a big one for motors and heavy industry.
It is. That's power factor correction. Most heavy industrial loads, think large motors, transformers, are highly inductive. Inductive loads cause the current waveform to lag behind the voltage waveform.
What does that mean in simple terms?
You can think of current and voltage as two people walking perfectly in rhythm. Induction causes one of them to start dragging their feet, making the whole walk less efficient. This lag means the grid has to supply more current to get the same amount of useful work done.
Which leads to more I²R losses all through the system.
Exactly. Unnecessary losses.
So how does a capacitor fix this?
Well, a capacitor is a capacitive load, which does the opposite. It causes current to lead voltage. So by adding a strategically sized capacitor bank to the system, you're essentially injecting this leading reactive power to cancel out or neutralize the lagging reactive power from the motors.
To get them back in sync.
It pushes the power factor closer to unity, or 1, ensuring current and voltage are moving in sync. This maximizes efficiency and minimizes grid losses. It's a huge deal for industrial consumers.
And finally, its critical role in starting common household appliances.
Right. The third function is creating phase shifts for starting single-phase motors. If you only supply one phase of AC power to a motor, it just creates a pulsating magnetic field, not a rotating one.
So the motor would just hum and not turn.
It would just sit there and hum. It needs that rotational force to start. The capacitor creates a necessary current phase shift in one of the motor's windings relative to the other. This creates a temporary, effective second phase.
And that gives it the kick it needs to start spinning.
It gives the motor the starting torque it needs to get going. Without that little capacitor, your ceiling fan would be useless.
Let's end this physics section with a very practical engineering problem. The water pump. Most residential pumps are centrifugal, right? They lift water by creating a low-pressure zone.
Correct.
So why do you sometimes have to pour water into the pump casing? Why do you have to prime the pump?
The centrifugal pump relies on the high-speed spinning of its impeller to throw water outwards, which creates a powerful vacuum at the center. Water is heavy and dense. The impeller can push against it and create sufficient suction pressure.
Okay.
The problem is that a centrifugal pump cannot pump air. Air is just too light, it's highly compressible, and it doesn't have the density needed for the impeller to create a strong, sustained vacuum, powerful enough to overcome atmospheric pressure and lift that column of water from deep underground.
So priming just ensures the pump has something dense to work with from the start.
Exactly. By filling the casing with water, you ensure the impeller has a dense medium to work with immediately. That allows it to start creating the necessary suction pressure to lift the water column from the source. It's a pure engineering solution to a very real physical constraint.
That kind of structural thinking is exactly what we need to apply now. We've gone from the flow of electrons to the flow of water. Now we need to zoom out to the flow of power across the entire nation, where those same conservation principles meet the very complex reality of economic demand. Transitioning to that national level, the scale is just staggering. The data from late 2025 puts India's total installed power capacity at somewhere around 505 to 510 gigawatts. That's a huge number.
It's a massive number, and within it lies a really remarkable achievement that I think often gets lost in the climate debate.
What's that?
India actually hit its COP26 target of having 50% non-fossil capacity 5 years early. We're now at roughly 51.5% non-fossil, which is about 263 GW.
And solar's a big part of that?
Solar alone is over 125 GW. This is a globally significant milestone. It proves the commitment to adding renewable capacity is real.
Okay, so that is the green milestone, a major capacity success story. But here's the paradox, and this drives the entire national conversation. Despite having over half our capacity as non-fossil fuels, mainly coal, still contribute 70 to 75% of the actual electricity generation.
The usable units of power.
Yes, the units that actually run the economy.
We have to be crystal clear on this point. The gap between installed capacity, the potential maximum, and actual generation, the energy produced over time, is the single most important metric for understanding India's energy dilemma.
And it's not a policy failure.
No, it's a reflection of operational physics, not policy failure.
Let's break down the why.
Okay. Coal provides reliable baseload power. It operates at high capacity utilization factors, or CUFs, typically around 55 to 65%. This means for every unit of capacity, it's reliably producing power for well over half the time, 24 hours a day, 365 days a year.
Yeah.
You can dispatch it on demand.
But renewables just can't do that.
Renewables, by their very nature, are intermittent. Solar only generates during the day. Wind depends on specific weather patterns. As a result, their utilization factors are severely constrained, often hovering between just 20 and 30%.
So you have all this capacity that's only usable a fraction of the time.
Exactly. Until we have massive, affordable storage, we cannot count on those 263 GW of non-fossil capacity to provide firm, continuous power, especially during the critical evening peak hours when demand spikes. The coal anchor is what prevents the grid from collapsing every single night.
So given that operational reality, why can't India just mandate an immediate phase out of coal, which is what many developed nations are pushing for? It really boils down to a fundamental non-negotiable choice, doesn't it? The pace of economic development versus the pace of decarbonization.
The sources outline a kind of trinity of constraints that make an abrupt coal exit impossible without severe socioeconomic disruption. The first one is the storage deficit.
Which we just touched on.
As we discussed, without massive, long-duration, affordable energy storage, which we just don't have yet, renewables cannot provide the firm power needed to stabilize a large, rapidly growing grid and fully replace coal's continuous output. It's a technological barrier.
And the second constraint goes right into the political economy of the major coal-producing states.
Yes, the massive employment dependence. Coal mining, logistics, power plant operations. This is the lifeblood of the economies in states like Jharkhand, Chhattisgarh, and Odisha. A sudden phase-out would trigger an immediate, devastating employment crisis.
So you need a just transition.
India requires a meticulously planned, sensitive, just transition strategy that provides alternative employment pathways before it can significantly accelerate the phase-down. Social stability dictates the pace here.
The third constraint is just the sheer overwhelming demand growth.
India's economy is booming, and the development needs of lifting millions of people out of poverty require massive, reliable, scalable, and most critically affordable power.
And right now, that's coal.
Right now, coal remains the most economically viable source to meet this current exponential demand growth. This is where the concept of energy justice comes in. We have to prioritize lifting populations out of energy poverty. We cannot impose the energy luxury choices of the developed world on a developing nation that is still building its foundational infrastructure.
So the strategy is a pragmatic duality. It's not about ignoring coal, but making the coal we use more efficient while rapidly building the foundation for the future grid.
Precisely. It's a two-track strategy. Track one is making the existing modern coal plants highly efficient and systematically decommissioning only the old, highly polluting, inefficient units. Track two is the aggressive expansion of renewable capacity, combined with strengthening the transmission backbone, the green energy corridors, to move that solar and wind power effectively.
So it's a dual approach.
Yes, designed to maximize development while minimizing environmental impact. It's driven by feasibility, not ideology.
We've established the generation is expanding, but the true Achilles heel of the Indian power sector has always been the distribution side, that final mile between the generator and you, the end user. We're talking about the distribution companies or discoms.
The discoms are not just the weakest link. They are the single greatest barrier to India achieving its net zero commitment. They're trapped in this iron cage of structural failures.
Like what? What are the big issues?
You have chronic, high aggregate technical and commercial, or AT&C losses, which is basically unpaid for power. You have massive tariff distortions that are imposed by state politics, subsidized power for agriculture, for instance.
And the state governments are often late paying for those subsidies.
Exactly. They delay the compensation for those mandated subsidies, and all of this results in these debilitating debt burdens that compromise the entire supply chain.
Let's focus on those AT&C losses because they really explain the chronic debt. Nationally, they're often quoted at 15 to 20%. That means up to 1/5 of all the power generated just isn't generating any revenue. What's the breakdown of those losses?
AT&C losses are a combination of two things, technical and commercial. Technical losses are the unavoidable physics. Power lost as heat from old, thin wires, inefficient transformers, long lines. A well-run utility can get these down to 5–8%.
Okay, so that's a small, manageable part.
Yes. The commercial losses are the existential threat. These are non-technical losses, and it's primarily theft, inaccurate billing, and poor collection of dues.
So when a state has 20% AT&C losses, maybe half of that loss or more is just outright theft or non-payment. That's not an engineering problem. That's an administrative and governance crisis.
Absolutely. The commercial losses are a direct measure of administrative failure and institutional weakness. The debt from these losses often balloons into tens of thousands of cores every year, and that prevents discoms from investing in the critical upgrades they need.
And how does this financial hemorrhaging on the distribution side directly stall the growth in renewable energy capacity that we were just celebrating?
The link is financial, and it's circular. Financially weak discoms cannot pay their bills on time. They delay payments to the generators, including the renewable energy producers, sometimes by months.
Which makes private investors very nervous.
It creates a massive financial risk premium that discourages private investors from financing new solar or wind projects. I mean, why would you invest billions when the only buyer for your product is habitually late on payments?
Right.
And on top of that, they lack the capital to upgrade their own infrastructure, the wires, the transformers, the software that's needed to absorb the variable power from renewables. In essence, the financial health of the discom dictates the operational ceiling for India's entire clean energy transition.
Previous schemes like UDA tried and largely failed to fix this. The current approach is the Revamped Distribution Sector Scheme, or RDSS. What makes this different from the old bailouts?
RDSS shifts the focus from a simple financial bailout to performance-linked funding and technological transformation. It mandates hard targets for reducing those AT&C losses.
And it backs it up with technology.
Crucially, yes, it backs this with massive central funding for technology, specifically the widespread deployment of smart meters to eliminate commercial losses through real-time metering and remote disconnection, and also major infrastructure upgrades to cut the technical losses.
So what's the key difference?
The key difference is the accountability mechanism. The funding is tied directly to achieving those performance metrics. It forces institutional change.
This brings us to the biggest proposed fix of all, the Electricity Amendment Bill. We framed the 2003 Act as a solution for a power deficit era. This new amendment is a solution for a distribution monopoly era.
That's the core context, yes. The 2003 Act was all about incentivizing supply. The 2025 amendment is aimed at optimizing delivery and ensuring financial viability. Its whole design is to introduce a fundamental structural change into a sector that currently operates as a state-owned geographical monopoly.
What are the three objectives that make this bill so transformative and so controversial?
First is delicensing distribution. This is the game changer. It would allow multiple private players to supply electricity in the same region, competing for your business.
Like with telecom companies.
Exactly like telecom. Second is the payment security mechanism. This mandates that discoms must post financial collateral, like a letter of credit, before power is even dispatched from the generator. This guarantees payment, breaking that chain of delayed payments that plagues the generators.
And the third objective deals with the lack of regulatory teeth.
Absolutely. Strengthening regulators. It empowers the central and state electricity regulatory commissions, the CERC and CERCs, with civil court powers.
So they can actually enforce contracts.
Enforce contracts, settle disputes quickly, and crucially, make sure tariff revisions are implemented in a timely way that reflects the true cost of supply. It removes the political ability to just endlessly delay cost-reflective tariffs.
But this bill has met with fierce resistance, mostly from state governments and their incumbent utilities. Why is this fight so politically fraught?
The resistance comes from two places: the federal structure and existential fear. On the federal concerns, states view electricity as a core component of their power under the concurrent list. They fear that central control over regulatory appointments and distribution standards is an encroachment on state autonomy.
And subsidized power is a huge political tool.
It's a key political tool used to support farmers and specific voting blocs. They don't want to give that up.
And the operational fear is this cherry-picking risk, that competition will only benefit the already powerful.
That is the greatest operational threat, cherry picking. The fear is that if private players are allowed to compete, they will logically only target the high-value, profitable customers' industrial units, big commercial centers, dense urban areas.
Leaving the state utility with all the unprofitable customers.
Exactly. It leaves the state discom saddled with the universal service obligation, the subsidized high-loss consumers, particularly in agriculture and remote households. The private sector privatizes the profits, and the state nationalizes the losses, which could lead to the collapse of the government utility.
I get to challenge the policy logic here for a second. Isn't this carriage versus content model where the government owns the wires and the private sector sells the power? Isn't that just an easy talking point that avoids the deeper political and financial problem? You're just transferring accountability for setting tariffs to a private company that can walk away if it's not profitable.
Yeah. That critique is valid, and it's really at the heart of this whole policy debate. The judgment, I think, is that competition is a lesser evil than the existing monopoly failure. The carriage versus content separation is designed precisely to mitigate that cherry-picking risk. By regulating the carriage, the physical wires, as a common carrier, the regulator can mandate access and ensure that the private content providers, the suppliers, pay an access charge that contributes to the upkeep of the network and to the cross-subsidization. The goal isn't pure privatization of assets. That failed in earlier attempts, like in Odisha. The goal is competition in supply, which, as we saw with the success of loss reduction in Delhi after privatization, forces efficiency, investment, and better consumer service. The policy has basically decided the benefits of competition outweigh the risk as long as the regulator is strong enough to prevent predatory practices.
So for the listener, this means I could theoretically choose my power supplier, like I choose my mobile provider, but the physical wires running to my house would remain the same common infrastructure.
Exactly. You're choosing the retail power supplier based on price or service or maybe green energy commitments, but the underlying physical infrastructure, the wires, the poles, the transformers, is still managed either by the incumbent utility or some regulated body to ensure universal access and network stability.
We've established the complex policy reality. But to truly reach net zero 2070, we need some radical technological solutions to solve these structural problems. And the first bottleneck, always, is energy storage.
Renewable energy integration is a massive systems challenge. It's not just about adding panels, it's about maintaining grid frequency and voltage stability despite the inherently intermittent nature of the sources. Solar and wind don't provide inertia, and they can fluctuate wildly from second to second.
This fluctuation is perfectly illustrated by the famous duck curve.
The duck curve is a great visual. It graphically shows the mismatch. You have massive solar generation during the middle of the day, creating the deep belly of the duck, which causes conventional power plants to ramp down severely.
But then the sun sets.
And as the sun sets, solar generation drops to zero, but demand, the head of the duck, surges as people return home and turn on their lights and ACs. Storage is the only viable tool we have to time shift that midday surplus solar energy to meet that crucial evening peak demand.
Without it, the grid just becomes unstable.
Right. Without it, renewable penetration beyond a certain threshold destabilizes the entire grid.
So what are the main constraints of our two leading storage options right now, batteries and pumped hydro?
Battery energy storage systems, or BESS, rely heavily on lithium-ion chemistry. The major constraint for India is cost and geopolitical risk.
We have to import the materials.
Lithium, cobalt, nickel. These are critical minerals that India must import, primarily from regions where supply chains are controlled by a very limited number of players. This creates a dependence that's dangerously similar to our past reliance on oil imports. It compromises our strategic autonomy.
And pumped hydro. That sounds ideal on the surface. It just uses water and gravity.
Pumped hydro is the cheapest form of utility-scale storage with a very long life, but it is severely location-constrained. It requires a very specific topography. You need two large reservoirs of dramatically different heights.
And that's not something you can build just anywhere.
Not at all. And it faces major hurdles with land acquisition, environmental clearances, and a gestation period that can stretch to a decade. We simply don't have enough ideal locations to meet the massive storage needs of the entire country.
So if lithium is expensive and geopolitical, and pumped hydro is constrained by geography, what are the emerging, more domestically friendly alternatives?
We're seeing focused research on alternatives that leverage India's domestic resource base. Sodium-ion batteries are highly promising.
Why sodium?
Sodium is abundant and cheap domestically. We can produce these batteries without relying on complex global supply chains. Now, they currently have a lower energy density than lithium, but they're safer, more stable, and perfectly suited for stationary storage applications like grid balancing and also for budget mobility like electric rickshaws and two-wheelers.
And what's on the more distant horizon?
The push continues toward solid-state batteries. They use a solid electrolyte instead of a liquid one. They promise far greater safety, higher energy density, and much faster charging rates. They're positioned as the future high-end solution for large passenger EVs, provided we can get the manufacturing cost down to scale.
To truly secure that 247 baseload without coal, nuclear power seems essential. This brings us to the proposed Shanti Bill. This legislation is seen as the biggest structural shift in the nuclear sector since the 1960s. What was the context of that original 1962 act that this bill aims to dismantle?
The Atomic Energy Act of 1962 was really a product of the Nehruvian era. It was driven by strategic autonomy and secrecy. It established a complete state monopoly over the entire nuclear fuel cycle and power generation.
And everything was funded by the government.
Yes. The underlying philosophy was strategic control, ensuring safety and preventing proliferation, with all funding coming from the central government.
And why is that model untenable today? Why is the government being forced to open it up?
The shift is driven by massive cost and the decarbonization imperative. First, the fiscal constraint is just overwhelming. India is aiming for 100 gigawatt of nuclear power by 2047. The capital cost for traditional large-scale reactors is prohibitive, upwards of 15 to 20 crore rupees per megawatt. The government simply cannot fund that scale of expansion on its own. Private capital is essential.
And the second reason?
The decarbonization need. Nuclear is the only reliable 247 high-density green base load source we have. We need continuous carbon-free power to transition hard-to-abate industries like steel, aluminum, and cement away from fossil fuels. Nuclear provides the firm foundation that solar and wind currently cannot.
The technology that's enabling this private entry is the small modular reactor, or SMR.
Yeah.
Why are SMRs a better fit for private investment than the massive traditional reactors?
Traditional reactors are custom-built projects. They require massive capital upfront and can take a decade or more to construct. SMRs, which are generally under 300 milliW, fit the private sector profile perfectly because they are designed to be factory fabricated and modular.
So you build them in a factory and assemble them on site.
Exactly. This drastically reduces on-site construction time, it minimizes risk, and it lowers the initial capital expenditure, which allows for faster financial returns for investors.
And there's an advantage in where we can physically place them, too.
A huge one. The greatest strategic advantage is that SMRs can be plugged into decommissioned thermal plant sites. These old coal plant sites already have all the essential infrastructure: land, water access, and most importantly, high-voltage transmission lines connected directly to the grid.
So you bypass the two biggest hurdles: land acquisition and building new transmission lines.
Right, which can often double the cost and timeline of a traditional project. It's a massive advantage.
But we have to address the safety concerns. Opening up nuclear to the profit motive naturally introduces an element of risk. What policy mechanisms are being considered to maintain safety while still attracting investors?
The concerns are legitimate, absolutely. There's a lot of debate over potentially diluting the liability in the Civil Liability Act of 2010 to attract foreign suppliers. However, the government's stated plan is to maintain stringent safety controls while enhancing the regulatory framework itself.
Wow.
This involves strengthening the Atomic Energy Regulatory Board, AERB, granting it statutory independence, and significantly enhance civil court powers to enforce safety protocols with real teeth. The policy acknowledges that regulatory oversight has to be the most robust component of this new nuclear ecosystem.
We've now established the need for intelligent, clean power sources like SMRs and massive solar parks. But to manage these sources, which are intermittent and highly complex, you need systems intelligence. This means the grid is now reliant on silicon and software, which brings us to semiconductors.
Semiconductors aren't just components anymore. They are the brain of the modern energy grid and the engine of economic resilience. We have to understand the concentration problem. Why is manufacturing so dominated by East Asia, Taiwan, and Korea? And why is this so hard for anyone else to replicate?
It's a combination of time, money, and a very specific environment.
Precisely. It's the result of decades. We're talking 30 to 40 years of relentless, consistent state support, massive subsidies, tax breaks, protectionist measures. But even more critically, it's the development of the ecosystem, the cluster effect.
What does that mean in this context?
Fabs require infrastructure that is almost impossible to maintain elsewhere. You need ultra-pure water supplies measured in parts per trillion. You need a highly stable power supply. A nanosecond flicker can destroy an entire batch of chips. And you need the proximity of packaging, testing, and specialty chemical suppliers all in one place. This ecosystem is extremely hard to build from scratch.
India is trying to solve this with a 76,000 crore rupee national semiconductor mission, the NSM. What are the twin strategic objectives of this high-stakes initiative?
The objectives are rooted in national security and economic opportunity. First, strategic autonomy. We have to reduce our reliance on imported chips for critical sectors like defense, telecommunications, and high-end power electronics. The NSM aims to create domestic capacity for these strategic chips. Second, attracting fabs. The mission offers massive financial incentives, specifically a 50% capital subsidy to attract global foundry players. This is an acknowledgement that the startup costs are so incredibly high that without significant state backing, no major player will risk the investment in a new, unproven geography. It is the cost of entry into a geopolitical game.
We have to ask the direct question. How does chip security relate to our energy security?
The modern grid runs on chips. It's that simple. Renewables rely on power semiconductors in their inverters to convert and condition power efficiently. EVs use up to 3 times more chips than conventional cars for their battery management systems. And the very backbone of Discom reform, the smart meters and smart grid sensors, they all rely on sophisticated microcontrollers.
So if there's a disruption,
If geopolitical tension cuts off our access to key power chips, the deployment of new solar parks stalls, the EV transition halts, and grid modernization becomes impossible. Therefore, ensuring a secure and reliable domestic supply chain for semiconductors is fundamentally an act of securing our future energy supply.
once we have that secure hardware, AI provides the intelligence layer needed to manage the grid's complexity, especially with all these variable renewables. How is AI moving beyond simple data crunching and actively solving complex engineering problems in the power sector today?
AI is now the optimization engine. One massive application is in predictive maintenance. Traditional maintenance is reactive. Something breaks, you fix it. AI analyzes real-time sensor data vibration, acoustic signatures, thermal mapping of transformers to predict when a component is going to fail, days or even weeks in advance.
So you can fix it before it breaks.
It allows for scheduled, targeted maintenance, preventing catastrophic blackouts and extending the life of your very expensive capital assets.
And what about its role in solving that notorious duck curve problem?
That's the second crucial application: real-time grid balancing and forecasting. AI algorithms ingest vast amounts of data weather reports, historical demand, solar radiation levels, wind velocity to create highly accurate near-term forecasts. It then automatically optimizes the generation mix,
So it's making decisions second by second.
deciding in real time whether to ramp up a flexible hydro plant or curtail solar output because of predicted cloud cover, or charge or discharge a battery. It manages the instantaneous fluctuations that human operators simply cannot track. And the third application directly impacts the financial health of the discoms: automated theft detection. By analyzing patterns in smart meter data usage anomalies, sudden zero readings, weird correlations, AI can flag non-technical losses and suspicious usage that are totally undetectable by manual audits.
Allowing for highly targeted enforcement.
To recover that lost revenue, yes.
This era of interconnected intelligent machines is often called Industry 4.0, the age of cyber-physical systems. And while it brings all this efficiency, it also poses a massive structural risk for a labor surplus country like India.
Industry 4.0, where everything from factory floors to utility systems is integrated via the Internet of Things, presents the risk of what's being called premature deindustrialization.
What does that mean?
It means if advanced robots and automation become cheaper and more reliable than human labor, global manufacturing may bypass the traditional labor-intensive growth phase that India needs to employ its massive young workforce. Developed nations could potentially nearshore manufacturing because of automation efficiencies.
So India's opportunity must be in managing the intelligence, not just providing the labor.
Exactly. India's opportunity is to leverage its strength in IT and software to become the global control center for these autonomous factories and smart grids. But this requires a rapid, comprehensive national workforce reskilling effort, moving people from repetitive tasks to high-value roles in system design, maintenance, and data management.
But this digitalization radically expands the grid's attack surface. The 2020 Mumbai blackout, whether it was state-sponsored or not, really highlighted the danger of a cyber-physical threat.
Digitalization moves the threat vector from a physical break-in to a remote cyber intrusion, and that increases the risk of a cyber Pearl Harbor. A coordinated attack could exploit vulnerabilities in smart meters or control systems to cause cascading physical damage like tripping substation breakers or destroying transformers, leading to widespread blackouts and economic chaos.
So what's the solution?
The solution is a defense-in-depth strategy combined with policy. Technically, this includes islanding schemes, which are control systems that can automatically detect a major system failure and isolate that section of the grid into a self-sustaining microgrid, preventing the failure from spreading.
And the policy side?
Policy-wise, it requires enforcing strict regulations that mandate critical hardware and software for the power grid must be sourced only from government-vetted, trusted sources, which mitigates the risk of supply chain espionage.
From securing the power grid, let's look at securing the information grid. Deepfakes represent perhaps the most immediate critical threat to societal stability and democracy.
The core ethical concern here is the violent erosion of trust and the violation of consent. Deepfakes allow bad actors to use a person's likeness, their voice, their behavior without any permission, and it destroys the fundamental basis of seeing is believing.
It creates an accountability crisis.
It does. Real evidence can be dismissed as fake, and manufactured lies can be treated as fact.
And in the political sphere, this danger is amplified by the sheer speed of modern digital dissemination.
They weaponize the instantaneous speed of social media against the comparative slowness of institutional truth. Imagine a deepfake video showing a high-profile official engaging in some treasonous or inciting behavior released strategically just hours before a major election.
By the time it's debunked, the damage is done.
By the time fact-checkers and official bodies can debunk the sophisticated fake, a process that can take days, the political or electoral damage is already catastrophic and irreversible. Deepfakes enable targeted, instantaneous disinformation campaigns designed to destabilize political processes.
We've covered everything from fundamental physics to strategic national technology. Let's conclude by looking at the future of personal mobility and the mindset required to administer these massive interconnected systems.
The transition to electric vehicles is a global necessity, but in India, we have to analyze the will-to-wheel debate. While EVs drastically cut down on local urban air pollution, which is a huge public health benefit, their global carbon footprint is entirely determined by the source of their power.
So if 70% of our power comes from coal, an EV is essentially a coal-powered car, at least for now.
That is the current reality. However, the immense benefit of the EV transition is that it is a future-proof technology. As India executes its net zero 2070 strategy and the grid incrementally decarbonizes year after year, the EV automatically becomes cleaner every single time you charge it.
Is there a break-even point?
Studies suggest that in India, the total life cycle emissions of an EV break even with a conventional petrol car after roughly 30,000 kilometers of driving. And that break-even point will only get lower as more solar capacity comes online.
Given the scale of charging infrastructure needed, is the immediate 0 to 5 year window better served by hybrids as a bridge?
The sources argue very strongly that hybrids are the most pragmatic bridge technology for the short to medium term. They offer exceptional fuel efficiency, often 25 to 30 kilometers per liter, and crucially, they eliminate the two biggest consumer hurdles: range anxiety and the lack of charging infrastructure.
So they buy us time?
They allow consumers to immediately reduce their consumption footprint without requiring the state to deploy massive public charging infrastructure overnight. It buys us vital time for grid modernization.
Finally, we have to revisit the Tesla deadlock. This is a high-profile negotiation involving high-stakes geopolitical trade-offs. Why has this stalemate persisted for so long?
It's a classic conflict between market access demands and domestic industrial policy goals. Tesla's position is purely about market testing. They want a massive reduction in import duties, which can be up to 100% for fully built units, so they can gauge consumer interest before committing billions to manufacturing here.
And India's Make in India stance is non-negotiable.
It's non-negotiable. Any significant tax concessions are contingent upon a concrete commitment to local manufacturing. India refuses to be merely a market for finished goods. It wants to be a producer of high-tech manufacturing, ensuring job creation and technology transfer. The stalemate persists because neither side wants to give up its strategic leverage.
Let's pull the lens back one last time and reflect on the required administrative mindset. We've seen that almost every problem, from Discom debt to SMR deployment, involves engineering constraints interacting with social variables. What is the core benefit that the systematic training of an engineer brings to administration?
The core benefit is structured thinking and the ability to identify constraints. And engineers train not to provide ready-made answers, but to systematically diagnose a problem, to accurately identify the critical limiting variables, be they financial, technical, or social, and then to design feasible, optimized solutions.
And that's invaluable in public systems.
When you're dealing with complex, interdependent public systems, the scientific temper and structured approach are invaluable for planning, for implementation, and for monitoring outcomes.
To illustrate this systematic approach, let's use the practical example from the sources: managing a power restoration crisis after a severe cyclone. What is the administrator's protocol for prioritizing restoration?
The protocol is a strict triage hierarchy based on risk and necessity, not on convenience. Step 1 is always safety first. Immediate isolation of all snapped live power lines to prevent electrocution and public tragedy.
Before you do anything else.
Before anything. Step 2 is critical infrastructure, restoring power to hospitals, command centers, and major telecom switches to ensure communication and life-saving operations can continue.
Yeah, what's next?
Step 3 focuses on water and health, powering up municipal water pumping stations to prevent the collapse of public health services due to a lack of potable water. Only after these existential needs are met, in Step 4, does the focus shift to residential and commercial areas, systematically restoring feeders based on density and feasibility.
It's a structured, risk-based approach.
That is the essence of sound engineering judgment applied to public administration.
And finally, the policy philosophy driving this massive, complex energy transition. It has to be dictated by a principle of energy justice.
That is the ultimate ethical and pragmatic policy judgment. India's strategy must be dictated by energy justice. We have to acknowledge that developed nations must lead the way, but India must maintain its right to development.
So the strategy is a balance.
It's a balance between leapfrogging, like the mass adoption of solar, skipping grid dependency in remote areas, with the pragmatic reliance on coal for baseload stability. We are charting a self-determined path that balances energy security, affordability for the masses, and our long-term global sustainability ideals.
What an extensive deep dive. We spanned the physics of the I-squared-R law and the exponential efficiency of the transformer, all the way to the monumental challenge of moving 70% of a nation's energy generation away from coal.
It's a huge undertaking.
We established the crucial role of Discom reform through RDSS and the existential need for storage to manage that capacity versus generation paradox. And we explored the high-stakes strategic importance of technologies like small modular reactors and the National Semiconductor Mission,
which are absolutely foundational to the 2070 net zero goal.
Absolutely.
The overarching takeaway is that success in this energy and technology transformation is predicated on building complex policy solutions upon rigorous engineering constraints. Our future solutions must not just be technically viable, they have to be economically, socially, and politically feasible for a developing nation that prioritizes energy justice and mass affordability.
So the administrative mindset has to be structured.
Let's be structured, systematic, and always focused on navigating those trade-offs.
That is the perfect summary. To close out this deep dive, we want to leave you with a final provocative thought to consider.
We saw how the Electricity Amendment Bill introduces market competition to power supply, similar to the logic that transformed the telecom sector. However, electricity cannot be buffered like data. A grid failure is physical, instantaneous, and catastrophic. Given this high technical risk and the parallel, pervasive ethical concerns around weaponized deepfakes eroding information trust, how must governance, law enforcement, and regulatory bodies evolve to handle a world where both our essential physical infrastructure and our core information are instantaneous, interconnected, and highly vulnerable to sudden collapse or malicious manipulation?
A question worth chewing on for the rest of your week. Thank you for joining us for this extensive deep dive. We'll see you next time.